Number 4, we have to reverse the order of integration on this, so we want to go dx dy, and to do that we need to sketch the region that's involved. So let's see what we have. So this, since dy is first, this is saying that this first integral is showing us the region. The region is bounded by this curve and this curve, which is y equal x squared, and it goes this way as well, y equal 4, which is a line. Okay, and then the x is going from x equals 0 to x equal 2, and we can see that 2 is right here because when I put in 2, that's when I get 4. So the region is this region. And so to set it up in the other direction, which is this direction, I'm going to be doing the x first. And so x, we can see, is going to start at 0. It'll go out till it hits this curve. That's the curve y equal x squared, but I got to solve for x, so it's going to be x equal plus or minus the square root of y, but we can see we're on the positive. This is generating the positive x's. So this is going to be x equal square root of y. And then the y is we're going to put the strips in here, stack them in from 0 to 4. And then this next one, it says to use polar coordinates to set up an iterated integral for, well, it's really the region we need to look at. This integral over a region that's formed by two circles. It's the region inside of this circle, which, as it says, is a circle that's passing through 2 and the origin on the y-axis. And then it's a circle centered at the origin of radius 1. So in other words, it's a circle centered at 0, 1, has a radius of 1. But we know that's one of our nicer polar regions that we can write the equation down for. So here's what I've got. I've got a circle that passes through 2 and the origin. And then I've got this other circle of radius 1. Just going to do something like that. I'm not that worried about centered at the origin. So it's inside this circle, but outside of that circle. So this is the region here that we have to set up. And we're going to do it in polar coordinates. So we know that what this means I need to do is I need to change my x's to r cosine theta. I need to change my y's to r sine theta. So if I had an actual function, I would do that. I'm just indicating it here that I would do that. And then I do r dr d theta. And so we draw a strip across this region from the pole. So I start at the pole and I go out. I'm going to make it a dotted line because I'm not in my region yet. So right there is where I start hitting my region. And so I need to figure out what limits this indicates, because this is telling me what my r is doing. My r is going from this boundary, which is obviously that circle of radius 1, out to this boundary, which is my offset circle. So my r is always starting at 1. No matter where I draw that strip, it's always going to start at 1. And then it always stops when it hits that outer boundary. Well, we have to write that in polar coordinates, but the circle that goes through 2 and the origin on the y-axis is 2 sine theta. You can get that by multiplying this all out. You'd end up with this x squared plus y squared, and then you'd have a 2y minus 2y plus 1 equal 1 on this side. The 1's cancel, so you'd end up with x squared plus y squared equal to 2y. But now that's an r squared, and that's 2r sine theta, because y can be turned into r sine theta. And then to divide out the r, and you get your r equal 2 sine theta. So it's easier if you just remember what it is, because it goes through the origin and 2. And then I got to figure out the thetas. So we can see that theta is going to start here, whatever that angle is, and it's going to sweep this out like a windshield wiper until I get over here. And I can figure that out by setting these two circles equal to each other. So I've got that 2 sine theta, that's r, equal this r, which is 1. So it's a little bit of trig. I got to figure out when sine theta equals 1/2. Well, we can draw a triangle because this is opposite over hypotenuse in some right triangle, at least for the reference angle theta. And that triangle looks something like this. It's 1, 2, so this would be square root of 3 if you use the Pythagorean theorem, and that means I'm in the position of the angle, which is pi over 6. So in quadrant 1, that is pi over 6. So that's this lower limit. But in quadrant 2, sine is also positive, and what I'm getting there is this angle is pi over 6. And therefore, this would be 5 pi over 6 if I go to that angle, because that's where it stops, is at that angle. So the upper limit would have to be 5 pi over 6. And that would be your double integral in polar coordinates.